Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it is my pleasure to introduce Ahmed Eldawi from the University of Minnesota. He's a Mohammed Mokbil student. So he has been working on spatial Hadoop for some time now, and this work has had phenomenal impact across the open source community with multiple downloads and real customers and stuff like that. So it's very interesting. And he's also, apart from that, he had 2 successful internships at MSR as well as an internship at IBM in Watson as well. So let's get started. Thank you.
Okay, thanks, Patrice, for the introduction, and thank you, everyone, for taking the time to attend the talk. So my talk will be mainly about the work that I've been doing during my PhD, which is around Spatial Hadoop and MapReduce framework for big spatial data. And before getting into the details of this, I'd like first to give an overview of my PhD journey. So actually, since my work was mostly related to spatial data, I prefer to show it on a map like this. So I actually I got my bachelor's and master in Alexandria University. And at this time, I also co-founded Badra IT, which is a software company headquartered in Alexandria, which is still, by the way, running and still growing since I started it. And then I moved to Minnesota, where I did my master there, started my PhD program there. And on the first year, I used to work with other senior students in my group on problems related to recommendation systems. And I also get the chance to participate in the Sigmund programming contest on this year, and I actually got selected as one of the finalists and presented my work in Sigmund on that year. After this, I had a summer internship in IBM, where I actually worked on clustering of streaming graphs on that year. And after this, I returned back to Minnesota for just 1 semester, where I worked in SendBed, which was a location-based social network a project that we started in Minnesota at that time. After this, in the spring, I moved to QCRI, where I had an internship there for data cleaning, which is a system called Nadif. And then I came here to Microsoft Research. That was my first internship here in Microsoft Research, where I worked on Hackathon with Paul Larson and Justin Lewandowski. And then I returned back to Minnesota, where I spent 1 year in Minnesota at that time. And actually, in that year, I released or launched the first version of Spatial Hadoop. And I published a couple of papers about the different aspects of Spatial Hadoop, the different components of it, and some demos about it as well. After this, I went to the GIS Innovation Center in Saudi Arabia, where I spent 1 year there starting the center. It was actually starting on that year. I did a couple of projects there that are related to my PhD topic, and they are still working on these projects now. After this, I came here back for Microsoft Research, where I did my second internship here. And this time I worked with Patrice and Jonathan on Quill, which is a distributed processing engine for streaming data. And then I finally returned back home to Minnesota, where I continued the work I started in Spatial Hadoop and published other works about this, and also started HadoopViz, which is a visualization framework that I'm going to describe also in this talk. And then also during this time, I had a short trip to University of California, Irvine. That was like a 1 month visit to Mike Carey group there, where I worked on AsterixDB. And actually, the final outcome of my PhD was quite prolific from all these trips and different visits. So I actually, if you see my Google Scholar stats, I had more than 550 citations for my work. And I did a couple of journal papers, conference papers, demos in top database conferences and journals. And I also conducted some tutorials about the work that I've been doing. And I also had the chance to collaborate with more than 35 collaborators from 6 different institutes. So without further ado, let me start describing the work that I have been doing in my PhD. And before getting into the technical details, I would like first to give a story. This story is actually between the people in computer science and people in geography, which started a long time ago, when people started to create maps. And they continued this map to create different maps, bigger maps for the whole world with different projections, different applications, such as, for example, medical applications or urban planning. And this went on for a long time until earlier this last century, something happened. The computer was invented. And the computer, it came as a disruptive technology. It changed the way you think about their work. And then we have these 2 parallel worlds for some time. and each one worked on its own, until at some point, this guy from geography thought about using computer. So I said, I have big data and I need help. It was big data at that time, although it's not as big as we know it today. So he talked to the computer science guy and told him, cool computer technology, can I use it in my application? And of course, people in computer science are not to be very nice. So I said, my pleasure, here it is. But it was not that easy. There was a problem, actually. He said, it's not made for me, and they can't make use of it as is. So we have a gap between these two worlds, and someone needs to step in and fill in this gap. So this is Jack Dangermond, who founded Esri. He talked to the computer science guys, told them, kindly let me get the technology you have, and to the geographers, kindly let me understand your needs. And then he sat with his friends and founded Esri as one of the first companies that work with the geographical data on computers. And now we have 3 parallel worlds, and as the time went on, each one started to grow on its own. So this is Jim Gray, who one of the main founders of System R, which became the seed of the database management system field. And it was very successful. It was used in many open source and commercial software and in many applications as well. At the same time, Jack Dangermond continued his work in Esri and released the first version of ArcGIS running on a PC. In the geography world here, we have my good child, who is currently a professor at Santa Barbara. And he made use of these new technologies to advance the field of geography. Again, this went on for some time, until at some point, this guy from geography started to scream out again. So he said, I have big data, and your technology is not helping anymore. So Jack still maintained his connection with the computer science world. So he said, let me check with my good friends here. So he talked to this database guy. He told him, cool database technology. Can I use it in my application? Again, the nice database guy said, my pleasure. Here it is. But the same problem happened again. He said, it's not made for me, and they can't make use of it as is. So now, again, we have this gap between these two worlds, and someone needs to step in and fill in this gap. So this is Hanan Samit, who is currently a professor at Maryland. He talked to the database guys, told them, kindly let me get the technology you have, and again, to the geographers, kindly let me understand your needs. And then he founded the area of spatial DBMS. And now we have 4 parallel worlds. And again, as the time went on, each one of these guys has his own success stories. So Jim Gray got the SM Turing Award for his work in databases. It was used in many commercial software and open source software. Hanan Samit became a very successful professor at Maryland. And most of the work in spatial database was used in many of these commercial software. Also, Jack Dangermond is currently a multi-billionaire, and his company is the #1 company in the area of GIS and geographical processing on computers. Also, my good child is currently an emeritus professor at Santa Barbara, and he directed and founded the first National Center for GIS for 20 years. And he, again, made use of all this new technology to advance the field of geography. This, again, went on for some time, until earlier this century, something happened in the computer world here. So this is Jeff Dean from Google, who invented MapReduce. And he actually, it became very successful. Actually, he got the National Academy of Engineering for this work. And it was used in many other software and other research projects in different areas in other companies. At the same time, with the Web 2.0 technology and the smartphones and the new satellites, people in geography started to have unprecedented amount of data that they want to process. So again, this guy from geography started to scream out again. He said, again, I have big data, and their technology is not helping me anymore. So at this time, Jack knew the limitations of traditional DBMS. So he said, seems like the traditional DBMS cannot scale anymore for these applications, but he still maintained his connection with the computer world. So I said, let me check with my other good friends there. Now he talked to Jeff Dean. He told him, cool big data technology. Can I use it in my application? Now, what do you think Jeff would say at this point? He said, my pleasure, here it is. But the same problem happened again. He said, it's not made for me, and they can't make use of it as is. Now, what do you think should happen now? So someone needs to step in and fill in the gap between these two worlds. So someone needs to talk to the big data guys, tell them, kindly let me get the technology you have, and to the people in geography, kindly let me understand your needs. And we believe that SpatialHadoop is a system that fills in this gap. And this is what I'm going to describe to you in this talk. So the story that I have just described is all about geographical data. However, there are many other examples of spatial data that needs to be processed. For example, think about geotagged microblogs or geotagged tweets. These are data available in terabytes of data or trillions of points or records, and we need to make use of this big data technology to process it. Medical data, for example, like brain images or X-ray images. This, again, data is available in petabytes of data, and we need to process it efficiently using this big data technology. Smartphones, sensor data, satellite data. All these are very big data sets, and we need to process it. So when we started Spatial Hadoop, we thought about using Hadoop because it was actually the state of the art at this point. So we thought about using Hadoop to process spatial data. And we asked ourselves the question, can we actually use Hadoop to process spatial data? And the simple answer is yes. For example, you can express a range query in Hadoop like this, and it works fine. So for example, if you have a 60 gigabyte of data and you have 20 machines, it can process the data in 200 seconds. However, the real question is, can we do better than this? So what we ended up doing is that we married spatial data to Hadoop to get Spatial Hadoop out of this, where we can process or express the same query in a more efficient way. So we have a better way to express the query, but it's not only about the language. So it employs like efficient query processing, efficient indexing, which allows you to run the same query in just 2 seconds, which is 2 orders of magnitude better performance. You have a question? Yeah.
This might be a slightly detour. I'm going to ask the parallel database versus Hadoop question, especially given that there's a lot of prior work on building parallel spatial databases.
Right.
I think NCR has it, and almost all commercial database systems have spatial support. So
Right.
why not just use a parallel database version of that? No, I'm going to talk a little more about the trade-offs between that and Hadoop.
I'm not going to compare Hadoop to parallel database, but that's a good question. Like, why not using just the parallel database for this? The same question can be asked for Hadoop itself, right? So why Hadoop was out there? So the answer is that actually the case study or the use cases of Hadoop and parallel databases are a little bit different. So in parallel database, you have like this structured data, and you spend time for loading the data into the parallel database, build some indexes on it, and then run SQL queries on it. That's the case study. The other case study is Hadoop, which is like you don't have to pay the overhead of loading the data, but you have other types of queries that you run. For example, in Hadoop, you write MapReduce programs. And for MapReduce programs, you express other types of queries that cannot be usually expressed in SQL. So it's a little bit different case study. So what we're providing here is, if you are already using Hadoop and you are processing spatial data, and you're looking for a way to improve your queries, then you can use Spatial Hadoop. So it comes that for people who are already used to Hadoop, already decided to use Hadoop other than parallel database, and then they need to process spatial data. Yeah.
But Hadoop also lets you call into a database post query. You can join Hadoop with a database. So you could store your spatial data in a database, and with the rest of your processing in Hadoop and just join.
Right, like Hadoop DB, for example, right, where you can use an instance of databases in the underlying system and use it. Yeah, so again, it depends on the application or the case study you are looking for. So this works for some case studies, but there are other case studies where you want to write a MapReduce program. So if you use Hadoop DB, for example, you still write an SQL query, right? It's just another way to do a parallel database that relies on Hadoop. So depending on your case study, if you are interested in writing SQL programs for spatial data, then it's better to go for a spatial parallel database. If you're interested in writing MapReduce programs that analyzes big data, then it's better to use a Spatial Hadoop. So depending on your case study, you should decide which system to use. So now, what proposed here, Spatial Hadoop, which is like a next step of Hadoop that works with spatial data in a much more efficient way. And again, it's not just about like the high-level interface, but it actually modifies the core of Hadoop itself to better work with the spatial data. And this is what I'm going to describe in this talk. So in high level, Spatial Hadoop is an open source project. We actually released it in February 2013 as an open source project. And within 1 year, it was downloaded more than 80,000 times. And it got the attention of both industry and academia. So there are many big companies that approached us and showed their interest in Spatial Hadoop. And there are also many students, both undergraduate and graduate students in universities worldwide, who are interested in Spatial Hadoop. They are currently using it to do their research projects and their dissertation. We also had the chance to collaborate with different universities on research projects related to Spatial Hadoop. I'm going to just mention one example, which is the Cornell Lab of Ornithology. And although these are not computer science people, they still approached us and showed their interest in using Spatial Hadoop in a research problem they are working on. Other than this, I also conducted more than 5 keynotes, tutorials, and invited talks about Spatial Hadoop and my work in big spatial data. And other than the project, the open source project that we released, we also released more than 500 gigabyte public data sets, which people can use for benchmarking and testing their applications and their systems. Also, most recently, and after a year-long process with Eclipse Foundation, Eclipse Foundation incubated Spatial Hadoop as an open source project. It will continue as an open source project, but they will have additional community support and better respect for the project for the big companies to use it. And it has been renamed to GeoGenie for legal purposes, but it's essentially the same project. So I encourage everyone of you to try actually Spatial Hadoop, and if you are interested in it, I'll be happy actually to answer you. So providing like the open source, the code is open source. We're providing tutorials, instructions of how to install it, and tutorials of how to use it. So on this talk, I started by giving a motivation for the work of big spatial data and Spatial Hadoop. After this, I'm going to go into the internal system design of Spatial Hadoop. So I'm going to describe the core components of Spatial Hadoop. After this, I'm going to describe some applications that we used Spatial Hadoop to build. And then I'm going to go quickly over some related work and some experimental results of Spatial Hadoop. Then I'm going to go quickly over other research projects that I have been working on and my future research plans. So let's start with the overall architecture of Spatial Hadoop. So you have multiple layers inside the system that are designed to work efficiently with the spatial data. At the lowest level, we have an indexing layer. And in the indexing layer, we are concerned of storing big spatial data sets efficiently in a distributed file system. So we have a big file that contains spatial data, and we need to store it in a distributed environment. And we need to see the best way to process it or store it. On top of this, we have the MapReduce layer. And in the MapReduce layer, we want to extend the MapReduce query processing engine so that it can access the underlying indexes. So you still write a MapReduce program, but you want to have some access methods to the underlying spatial indexes. On top of this, we provide an operations layer. And in the operations layer, we encapsulated a wide range of spatial operations that are built efficiently and make it to the indexing and MapReduce layers to run much more efficient than traditional Hadoop. Then on top of this, to hide the complexity of the system, we are providing a high-level language called Pigeon, which has spatial constructs and hide the complexity of the system. It makes it actually available for non-technical users to use the system. We also recently added a visualization layer where users can interactively explore big spatial data sets efficiently in a kind of visual interface. Also, with a recent interest like in spatiotemporal data, we add on the side ST Hadoop, which is an extension that goes across all these layers and adds efficient processing or support for spatiotemporal data. On top of the system, we have a wide range of applications that use Spatial Hadoop as a backbone to process big spatial data. So in this talk, I'm going to focus on the indexing, operations, and visualization layers. And I'm going to go quickly over some applications that we built using Spatial Hadoop. So let's start with the indexing layer. And again, for the indexing layer, we have a big spatial data set, and we need to store it efficiently in a distributed file system. So let's first see how traditional Hadoop loads a big data set in the HDFS, or the Hadoop distributed file system. So if you have a big file like this, it chops it down into blocks of 64 megabytes, and then put each block in one of the machines. However, when it does this chopping down, it doesn't take the values of records into account, which means that spatially nearby records, such as like relevant records, will end up in two different machines, which will reduce the performance of the query processing. And if you wanted to use one of the traditional spatial indexes, such as R3 or Quad 3, they cannot be applied as is in HDFS, because HDFS is too restrictive as compared to the traditional file system. Once you write a file in HDFS, you cannot modify it. So this becomes as a limitation by design in HDFS, which is totally different from traditional file system. So we cannot make use of the traditional indexes as is. And at the same time, the data sets we work with are really huge, so we cannot just load all the data in one machine and let it partition or spatially index the data efficiently. So what we ended up providing in Spatial Hadoop is a two-layer index design, which overcomes these limitations. In the first layer, we have a global index, which again partitions the data into blocks of 64 megabytes, but it puts nearby records in the same block. So each block here will contain records that are spatially relevant or spatially nearby, which will improve the query performance, as we are going to show shortly. Yeah.
You only consider 2 dimensions, right? The geo is always 2-dimensional data.
It's not always 2-dimensional. What we proposed, if you talk about the concept, they can actually apply to higher dimensions as well. So we're using like concepts like R3 and Quad 3, which can run at higher dimensions, while the version that we released in Spatial Hadoop is mainly 2-dimensional, because this is like the types of data set that we had access to. Yeah.
We're expecting the data to be schematized.
Sorry.
The data, how do you know it's lat long? It's just a file.
So I just had like 2 dimensions, and I deal with it as like an Euclidean space.
So you expect the location information to be declared.
Right. Yeah. So there is like let's say a spatial attribute which can contain not just points but can be rectangles or any like polygons or lines, and we process this attribute to process the data or partition the data. So Ravi, have a question?
It's a related question. So because the classic use case of Hadoop is I load the file, I don't know what to think about. It looks like you're replicating a lot of databasey things. There's a query language, there's an indexer, there is. So my question was, does the user have to worry about what columns to index? Does it vary for different spatial sets, or is it obvious? So it's sort of the questions they've been asking. So in a Hadoop world, you don't normally have to think about indexing, right?
Right.
So does it do something like auto-indexing? Does it understand which attributes is automatically relevant and index?
No, you still have to. So the question is how to find which attribute to index, right? What is the spatial attribute? Because typically when you load the file into Hadoop, it doesn't really understand the format of the underlying file. So in this case, if you are loading a data to Spatial Hadoop, we have to understand the underlying format, and the user has to define which attribute to process. So it could be like a point or polygon. So typically, like support different file formats. For example, if you have CSV files and they have a column in it which is like a polygon or line, then Spatial Hadoop can use this column to index the data.
As part of the data loading process, that you essentially define the schema that's going to result from building the index.
Right.
And it's assumed that the data is in a format that the scheme that will work for.
Right. So it's how the user needs to like define for each record how to get the spatial attributes out of it, which is basically just the MBR of this record. This is the main thing that we need to do. So it could be a different formats. Spatial Hadoop can work with different formats, but it needs to understand the spatial attribute of each record to be able to process the data like this, to partition the data efficiently like this. Yeah. So at the first level, we again partition the data into blocks of 64 megabytes, but we take the spatial attribute or the location of each record into account, and then again we load each one on one of the machines. As a second level, because each block of this is like 64 megabytes or 128 megabytes of data, so there is still a room for improvement or for better optimizing each partition. So we build a second level, which is the local indexes, where we organize records inside each partition efficiently. So now the real challenge here is actually how to find these boundaries of partitions. Because we mentioned that the data is really huge, so we cannot let one machine look at all the data and decide how to partition it. And at the same time, we cannot use the traditional ways of indexing or partitioning the data because of the limitations of HDFS. So when we started on this, we first thought about using a uniform grid to partition the data, which is very easy to implement, right? You can just scan the data and assign each one to the overlapping grid cell, but it doesn't work well with highly skewed data, which is the normal thing with spatial data. So it only works with uniformly distributed data. So we had to think of a better way of indexing the data. So we provided started with an R3 index, which I'm going to describe for you now, how to build the R3 index with these limitations. And we will actually quickly figure out how we can expand this work to support other spatial indexes. So at the first step, we first read a sample out of the data. So we have a very big file. We typically read a 1% sample of the data. And for this 1% sample, we just take the location of each record into account. So if you have a complex polygon, we just take its centroid, and which actually reduces the size of the data that we need to work on. So with 1% is a typical number. And for example, if you have like 100 gigabytes of data, with doing this sampling and converting to points, it can be reduced down to like 40 megabytes, which can be easily loaded into a single machine. The next step is that we let one machine load all this data, look at it, and then partition the space based on this sample. So this happens on a single machine, but typically takes a fraction of a second only because the data is very small as compared to the original data. So what this machine does is that it bulk loads all this data into an in-memory R3. But while building this R3, it adjusts the leaf node capacity using this equation. And the idea of using this equation is that it tries to adjust the number of leaf nodes in the tree that it builds to be equal to the number of HDFS blocks in the index that we are going to build, which means we'll end up with number of leaf nodes equal to number of HDFS blocks. And the next step is actually very interesting. So we throw away the sample because we don't need it anymore. And we also throw away the tree that we built. So we build this tree and then throw it away, but we keep only the leaf level. So we take the leaf nodes and take the boundaries of each leaf node as the MBR of the boundary of the corresponding block in the index that we want to build, which means we can easily scan the data, all the data now in parallel, and assign each record to the overlapping partition. So now we converted the complex index building technique to just scanning of the data, which can be done easily in parallel. And we don't have to worry about the limitation of HDFS anymore, because each record will go to, we'll know a priori which partition it will go to. As a final step, we can build a local index inside each of these partitions, and that's very easy because each block is typically 64 megabytes, so we can build all these local R3s in parallel. So this is actually how we build the R3, and I'm going to show you shortly that it's actually a very efficient way to build the R3. You have a question? Yeah.
So how do you ensure that the minimum bounding rectangles that you come up with will enclose 64 MB of data eventually?
We cannot guarantee this, of course, because I was just reading a sample. However, they can be slightly more or less than this. If it's less than 64 megabytes, then we'll have partially filled blocks. If it goes more than 64 megabytes, then we'll write multiple blocks for this partition. So some partitions can be slightly more than one block. Some of them can be half-filled or partially filled blocks. In reality, they are all very close to 64 megabytes of data. So this is actually how we build an R3. And now let me ask you a question. If we want to modify this algorithm to build a quad-3 index, do you know which steps we need to modify in this algorithm? So if you look closely, you'll find that there are only two spots or two places where we have R3-related logic, which is the bulk loading step and the local indexing step, which means if we take these two R3s and put quad-3s instead of them, we end up with a quad-3-based index. You can similarly build a wide range of spatial indexes using this technique. And this is exactly what we did next. So we built a wide range of spatial indexes. Okay, yeah.
So what is constraining you to use the same partitioning strategy as what you're building locally?
Nothing. You don't actually have to use the same one. I actually don't have to use both of them.
But the first problem is well formulated, right? Why build an index and then figure out the boundaries? Why not figure out the boundaries from first principles?
Sorry.
You can formulate a problem, algorithmic problem saying I want to find n rectangles where n is your number of nodes, where each rectangle, when scaled up by where sampling rate is about 64 gigabytes.
Right. And this is actually the
formulated problem. You don't need to build an index to solve the problem. Like maybe there's a better algorithm to do it.
Right. So what you're mentioning is totally right. Like the problem is how to find these boundaries of partitions. The index is just a solution to this problem. So what I'm showing here is actually the solution of the problem. But what you're mentioning is correct. So the problem is actually at higher level, which is actually the same problem for indexing, for spatial indexing. So the main problem with spatial indexing has to partition the data into smaller parts and group nearby records in each one.
It's not obvious to me that the optimization condition is identical for indexing as for the partitioning. I've not thought a lot about this, so.
So basically, the basic idea of spatial indexing is to put nearby records together so that when you do query processing, you can quickly find which partitions you want to process or which parts of the data you need to process. If you use R3 or quad-3, they are just trying to solve this problem in one way. Of course, like on traditional indexing, you have also to worry about like insertion and deletion, which you are not worried about here. So just worried about this part, which you just partition the data into smaller parts.
So did you use like the FTR bulk loading technique or something like that?
Yeah, so for bulk loading the R3, we use the STR bulk loading technique. However, yeah, so this is just our solution, but you can definitely use any other kind of bulk loading technique. Like you can use R-star3, for example, or Hebel 3. Yeah.
So the spatial world is not converged on a good index structure. Why are we working on one? Why is your system supporting so many index structures? It's still an open problem. Like, are there too good, or do you need like 5 index structures?
Yeah. So the question is why we can support more than one index structure. I wouldn't say that it's like an open problem and we're still looking for other index structures or spatial index structures, as more as there are many index structures and there is no clear winner between them. Because once we have more than one dimension, you don't have like a linear order for the records. So some index structures are good for specific queries, and some other index structures are good for other queries. And this is actually what we did next. So we provided this wide range of spatial indexes, and we had a paper where we had an experimental evaluation that compares these different index structures. And what we found that there is no clear winner between them. So depending on the shape of your data sets, how they look like, and the type of query you are running, you can actually choose one of them. So think of it as like in traditional DBMS, we have like a hash index and B3 index and maybe bitmap index, right? So we have all these indexes in a database, And then the user needs to decide, or the administrator needs to decide which index to use based on the query they want to run. This is something similar here. So Spatial Hadoop is a system, like a big system that supports all the different kinds of spatial indexes. And depending on the queries that users want to run, they can choose the most appropriate or most used index for this. Yeah, so basically this is like the generic way of building the indexes, and users can easily add their own spatial indexes in this. So actually there are existing work that tries to add more spatial indexes to Spatial Hadoop. Now my next slide is actually my favorite slide in the indexing part, because it somehow summarizes the whole indexing story of Spatial Hadoop. So this actually shows you the R3 index that we built in Spatial Hadoop for a 400 gigabyte dataset of road networks. So you can see here that all the black rectangles represent 64 megabyte blocks of data. So for example, in the ocean here, because the data is very sparse, we have to get a very large partition. While in dense areas, like in Europe, for example, you have to get very small partitions to get 64 megabytes of data. And there are actually 2 points that I want to mention on this figure. First, that the idea of sampling and then bulk loading actually works. So you can see here that with just 1% sample of the data, we can still get a very efficient way to index the data. That's one point. The second point is that you can easily find now how Spatial Hadoop can be much faster than traditional Hadoop. So if you process this data in traditional Hadoop, and let's say your query is focusing on this area, you have to process all the data, right? Like this file contains like 10,000 partitions. You have to process the 10,000 partitions because you can never know which blocks you want to process. While in Spatial Hadoop, because we have these boundaries of partitions, you can limit the number of partitions that you want to process, and they can still parallelize them over multiple machines. And this is an example of R3, but we can also build like a quad tree, which will look like this. Or if you have uniformly distributed data, you can build a uniform grid index. And if you wonder how these data would look like if you load it into traditional Hadoop, I have this slide just for you. So you can see here that if you load these data in traditional Hadoop, almost all the partitions will cover the whole input space, which tells you now how Spatial Hadoop can be much more efficient. If you are processing a very small area here, you almost have to process all the partitions. So to summarize the indexing part, we mentioned the limitations of traditional Hadoop to build indexes, and we mentioned how we can overcome these limitations and provide a wide range of spatial indexes in Spatial Hadoop. Your question? Yeah.
Full-fledged indexing API, given the point you tell me which rectangle contains it, we just have the part. You just said you stored the leaf level alone, right? So it's not.
So the global indexing part. So it builds the bulk load the R3 and then takes only the leaf level. So it ends up with some kind of flat partitioning. This is the global index. So just for any record, it will put it in one of the partitions. The second level, which is the local indexing, will actually have like a hierarchical index structure.
If you have a filter predicate in your query, then you just scan the partitions which are relevant to that.
Exactly. So the global index is typically stored in main memory, which is like the boundaries of each partitions. So without having to process all this data, it can prune all the partitions that are outside the query range. So this is for range query. Although I'm going to mention other queries that we can run also within these indexes. So the next part, which is also very interesting and related to spatial indexing, is actually how to use these indexes in spatial operations. So if you're writing a MapReduce program for a specific spatial operation, how to make use of these indexes in this. And actually, Spatial Hadoop ships with a wide range of operations. We started with basic operations such as range query or k-nearest neighbor, and then added more like spatial join operations and a wide range of computational geometry operations, such as convex hull, polygon union, Voronoi diagram, construction, or Delaunay triangulation. And this actually layer is extensible. So if users are interested in adding their own operation in MapReduce, they can just write their own operation in the same way that we wrote these operations. So I'm gonna mention some examples of these operations. Let's start with the range query, which is a simple operation. So you have a set of records, and you have a query range here, and you want to find the records that overlap with this query. So in this case, we can use the global index to prune the partitions that are totally outside the query range. And then for the remaining partitions, we can find the matching records efficiently using the local indexes in the matching partitions. So this is actually a very simple query, but tells you how we can make use of the 2 levels of indexes efficiently to run this query in MapReduce. Another operation is the spatial join operation. So we have 2 sets of records, and we need to find the overlapping records between the 2 files. In this case, actually, it's more challenging because you have 2 data sets, and each one is indexed separately. So you might have 2 different indexes. In a trivial case, if you have the same index used in the two partitions or the two files, then you end up with a kind of one-to-one correspondence between the partitions of the two files. So you just have this one-to-one correspondence, and then you can find the matching records in each pair of records efficiently. However, in reality, this case almost never happens. Because in reality, you have two files, and each one is indexed separately. So you end up with two different types of indexes. For example, even if we are using a uniform grid index, we'll end up with like a 3x3 grid and 4x4 grid for these two files, depending on their sizes. And now we have two ways we can continue the spatial join query processing in this case. One way is to do the join directly. In this case, we will find the overlap between the two partitions. And for example, in this case, we'll find a total of 36 overlapping pairs between the two indexes. So each pair of blocks or each pair of partitions will be processed in one of the machines to find overlapping records. That's one way. The other way is to do partition join. So in this case, we will repartition one of the files. For example, we will repartition the 3x3 grid, the reverse file here, to be a 4x4 grid, which exactly matches with the other file. This takes us back to the trivial case where we have one-to-one correspondence. And we'll end up with only 16 overlapping pairs of partitions between the two files. Now, the challenge is actually which one to use out of these two algorithms. So if we do the join directly, we don't have to pay the overhead of repartitioning, but we might end up with a huge number of overlapping pairs. While in the partition join, we have to pay an overhead of repartitioning one of the files, but we minimize the number of overlapping pairs. So based on this, we actually equipped SpatialHadoop with a cost model, which compared the cost of the two algorithms and then decide which one to use for a specific query. So this actually takes into consideration the number of partitions in each file and the number of overlapping pairs of partitions between the two files. So the cost model is actually ends up to be a very simple rule-based model here. So another class of operations is the computational geometry. This actually started all with the polygon union operation. There was actually a marketing team in a company that approached us and showed their interest in using SpatialHadoop to speed up this query, the polygon union query. And then we continued on this and provided a complete library of computational geometry work in SpatialHadoop. So we added the skyline operation, convex hull, farthest pair and the closest pair. Recently, we added Voronoi diagram construction and Voronoi triangulation. And all of them are done efficiently using the spatial indexes that we build in SpatialHadoop. So in all these operations, we start with a single machine as a baseline here. And then we started by providing a Hadoop implementation for these algorithms. So for each of these algorithms, provide a Hadoop implementation, which does not use the spatial indexes, but still parallelize the work using MapReduce. And we got up to 29x better performance for this is actually for the skyline operation over 128 gigabytes of data using 20 machines. You have a question?
What are some example queries which call these operations?
Sorry?
What are some example queries that require these operations?
So skyline, for example, so you have like say you have billions of points and to find the skyline of these queries. You are talking about like real applications that can use this huge data set? So I'll give you just one example. For example, is the Voronoi triangulation. So the Voronoi triangulation is actually used to triangulate the space based on the distance between points. And this is actually used to model the surface of the Earth. So you have like LiDAR data, which tells you the altitude at different points in the whole Earth surface. And to have a better model for the whole Earth surface, you have to find the Voronoi triangulation of all this data. So like we have huge data sets for this. We have billions of points, and we need to find the Voronoi triangulation of all this to find a good model for the Earth surface. So this is one example for this.
So this would be so that you can do, for instance, a more accurate spatial join or something like that of two data. So what's the value of having the triangulated, surface? It's really almost like a 3D model topology or something like that.
Exactly. So you have the points, like you have the altitude of different points on the Earth's surface, and you need to estimate the points, the altitude at other points. So the way they do it is that they do first the Voronoi triangulation, and now let's say you want to estimate the altitude at this point. Then you take into account these 3 points that form the triangle around it. And then, so for example, you have a point here. You don't have the altitude at this specific point, but you can estimate it by taking this altitude, these 3 points into account.
So if you want to know that Denver is a mile high or something like that.
Right, yeah.
Okay.
Yeah, exactly. Yeah.
So with the 20 machines, you got a 29x speed up?
Yeah, actually, they are 20 machines with dual cores, so we have like in total 40 cores. Yeah. So we started with this, which is just like a parallelization of the existing algorithms. But we didn't stop here. We continued by providing a more efficient algorithm that uses the spatial indexes into account, and we achieve up to 260x better performance for the same application or for the same query in this case. Yeah.
Data set size of 128 gigs, right? That's not very big.
Right.
You're saying data set is 100 gigs.
Right. Yeah.
Have you tried to switch?
We tried. Well, not with the computational geometry, but for other parts, we tried up to 5 terabytes of data. Basically, we were actually limited to the resources we had in this, because we had to run these on an internet cluster that we have in the university, and it was not that big at this time. So we only had 20 machines, and each machine had 50 to 100 gigabytes of storage. So it was not really very huge because you have to do the replication and all this stuff.
But you mentioned that some of the users are indexing petabytes of data. Is that right?
Yeah, that's actually one of the things that we are going to mention later, which is the visualization part. So with visualization, we tried up to petabytes of data and trillions of points, basically.
Can you try comparing against the parallel DBMS version that has spatial indexing and optimization built in? Because in a sense, what you're saying is you're as Ravi was pointing out earlier, you are doing a lot of the pre-processing and indexing up front,
Right.
Just like you would in a parallel DBMS, right?
Right.
So either your cost has to be way lower in this setting, or your performance has to be higher, better, right?
Right.
How do you compare?
That's a good point. So we didn't actually compare to a parallel database, but we compared to a single machine database, and it was actually for example for indexing, for example, we didn't really compare in a experimental setting, but that was more of motivation for our work. So we had for example the 128 gigabyte dataset. We tried to index this using a single instance machine, which seemed to be possible, right? The dataset is not really huge, but it took a very long time. Sorry?
What is running on the single machine?
In this case, we are running these queries on the single machine. For example, we have let's say Dronoi triangulation. We have a set of points and we need to compute the Dronoi triangulation for all these.
But using which system? Just using a DBMS, single node DBMS?
Not even a DBMS, just like a Java program. So we just load all the data in memory and do all the query processing in memory. Yeah.
So is there a parallel DBMS with spatial support?
Paradise.
Yeah.
Paradise
NCR,
project.
NCR had.
It's an NCR act.
You may not get
I
access
think
to
Oracle also. Oracle supports this. Oracle Spatial.
Or is it single node?
I think it is, yeah. I didn't really use it, but I think, yeah. It's part of the DBMS, so if you can parallelize Oracle, then you can parallelize Oracle Spatial as well. Although we didn't really try to compare with these systems. But there are other work that compares Hadoop to parallel database. So we tried more here to compare Hadoop to Spatial Hadoop to show the effect of the things that we added in Hadoop. So I just want to show this. Yeah.
A lot of these numbers are highly specific to how you do MapReduce, right? Like how is Hadoop implementation, which achieved just 29x performance? How was it implemented? How did you partition the data? How do you map the data? How do you reduce it?
Right. So I'm going to show one example now, which is the convex hull. So I'm going to compare how it runs in Hadoop and Spatial Hadoop. I think this will answer your question. So in convex hull, we have a set of points, and we need to find the minimal convex polygons that contains all these points. Now let me show you how we implement this in both Hadoop and Spatial Hadoop. If we use traditional Hadoop, then we use the first step is actually partitioning the data. And if we use traditional Hadoop, we use the default or the traditional way of partitioning the data, which does not take the spatial attributes into account. While if you use Spatial Hadoop, we'll use the spatial partitioning as you see here. Now the next step is the pruning step, which can only be applied in Spatial Hadoop because it relies on the spatial partitioning. So in this case, we can prune this partition, which is completely outside the answer, because the convex hull will actually go around it. So we have a formal rule of pruning partitions here, and we can prune the partitions that will not contribute to the final answer. After this, we end up with a fewer number of partitions in Spatial Hadoop here, and in both systems, we compute the convex hull inside each partition. So this part is actually parallelized for both systems. However, Spatial Hadoop will be much more efficient because it can reduce the amount of partitions or the number of partitions that it needs to process, thanks to the spatial index or spatial partitioning that we proposed. Then the final step is to get the answers of all these local convex hulls and put them on a single machine to get the final answer. So this we can actually parallelize both the query in both Hadoop and Spatial Hadoop. But Spatial Hadoop is much faster because it can prune all the partitions that does not contribute to the final answer.
But the final answer should be small enough that it can write on one node, right? It's just a union of the connexes of each.
Right. For convex hull, this is typically the case. In other algorithms, such as Voronoi diagram, for example, the answer is typically larger than the input. So we have to use other techniques to do this work. I can discuss with you offline if you would like, if you're interested in this. So to summarize the operations part, we showed how we can make use of the spatial indexes to speed up different types of queries, which are all like implemented as MapReduce programs in Spatial Hadoop. Yeah, Fraga?
Convex hull in any number of dimensions.
The implementation is just 2 dimensions in this case. So another part that we added recently, yeah, question?
About these applications like Voronoi diagrams and so on, right? So are these now available as libraries that people can actually compose their larger MapReduce workflows where they're doing this and then maybe feeding it to a different part of their pipeline? So is that something that you're
Yeah, right. So currently, typically MapReduce, you run each phase as a MapReduce program. So we have like the MapReduce functions and the MapReduce program to construct the Voronoi diagram. Once you have the output, it's still stored in the HDFS, so you can run other queries on top of this or after this. Yeah, so all the operations are actually expressed as MapReduce, so which means you can have multiple phases out of this. So something we added recently is actually the visualization part. And in visualization, we have huge data sets, and we need to generate an image that describes how this data set looks like. So for example, if you have satellite data, we can visualize it like this. If you have road network, you can visualize it in a different way. And actually, all these different ways of visualization are already available. So there are existing algorithms for these types of visualization. The main limitation is that these existing techniques cannot scale to the amounts of data that we work with in Spatial Hadoop. So what we wanted to propose here is a framework called Hadoop Viz, which can scale out these existing visualization techniques. So in Hadoop Viz, we are not trying to propose a new visualization technique, but we are trying to scale out existing techniques so that they can work with the huge amounts of data that we work on in Spatial Hadoop. For example, this is an example of visualizing 1 trillion points, which represents the temperature in the whole world for over 6 years. So we have a daily snapshot. Each snapshot contains 500 billion points for the whole world. And then we have these available daily for over 6 years. And then we need to generate, in this case, we are generating 72 frames. Each frame represents the data in 1 month as one image. And then it shows you how the temperature changes over time. And although you can do this in a single machine, it will take around 60 hours to generate these 72 frames. While in Hadoop Viz, we can do it in 3 hours only using 10 nodes. So using a 10-node cluster. These are actually quad-core machines. So now let me show you how we actually visualize or generate each one of these frames efficiently in Hadoop Viz. So the basic idea is that we have a huge data set. We break it down into smaller parts, process each part separately, and then combine them together to get the final image. Now, there are actually 2 ways we can partition the data. Either we use the default Hadoop partitioning, which ships with traditional Hadoop, or we use spatial partitioning, where we add in Spatial Hadoop. If you use default Hadoop partitioning, we end up overlaying the intermediate images to get the final image. Yep. Sure.
We need to add any new algorithms. The existing tools, what you described earlier, should be enough, or is that not the case? Make changes to Spatial Hadoop to support the visualization beyond what you already described.
So basically, no. So we didn't add like new indexing technique, but we are showing like these are actually available as MapReduce programs. So this is actually basically how to write MapReduce programs that will generate these images efficiently. So we are using actually the same indexing technique or partitioning technique that we provided. Right. Exactly. Yeah.
You're moving up the stack.
Right. So this is actually on the top stack. So we are actually making use of the underlying components to build these visualization techniques. So if we use the default Hadoop partitioning, we end up overlaying the intermediate images. So think of this as like some transparencies. So we have multiple transparencies. Each one contains part of the image, and then when you put them on top of each other, you get the final image. While if you use spatial partitioning, we end up stitching the intermediate images to get the final image. So think of this as a jigsaw puzzle. So you have small tiles, and then you put them side by side to get the final image. Now the challenge is actually which one of these is more efficient. So we support both in SpatialHadoop or in Hadoop Viz. And actually, you can see that there is a trade-off actually between these two partitions. So the default partitioning technique is much more efficient than spatial partitioning because it doesn't have to take the attributes into account. But the overlay process is much more costly than a stitch process because the intermediate images are very large, so it has to process all these big images to get the final image. So what we ended up doing is that we proposed a cost model that compares these two techniques, and then SpatialHadoop or Hadoop Viz can automatically decide which one to use based on the image size. So what we found that as the image size increases, we better go to the stitch process, while for small images, the overlay process will be just fine. And based on this, we can actually implement an algorithm that can visualize each of these visualization types. And if you want to add a new visualization type, you can re-implement the algorithm for this. However, in practical, this is not really good because we'll end up with a huge number of implementations for the same algorithm, which is not good like for a product because we cannot maintain all these implementations. So what we ended up doing is that we proposed just one algorithm that can support all these different types of visualizations. And if you add a new visualization type, you don't have to modify this algorithm. And the secret here is that we provide visualization abstraction. So this abstraction contains 5 functions, and these 5 functions can be defined by the user or by the image designer to define the visualization logic. So you can define these 5 functions in a way to like visualize satellite data, and then you can define them in a different way to visualize, let's say, a heat map. So now we have a separation of roles. The image designers will focus on defining these 5 functions, while the role of Hadoop Viz is to generate the image at scale. So our concern now is just scalability issue. We don't have to worry about the logic of visualization. So now let me show you how the abstract algorithm looks like at a high level, and then I'm going to show some examples of how we can define these 5 functions. So the first step is actually to partition the data, and we mentioned the 2 ways we can partition the data. After this, we call the smooth abstract function, which is defined by the user. This basically takes nearby records in each partition and try to fuse them together to get a better looking image depending on the visualization logic. Then we call a create canvas abstract function, which initializes an in-memory data structure that can be used for plotting or visualization. Then we call a plot function, which takes one record at a time and updates this canvas to draw or plot the record on this canvas. So again, this is an abstract function defined by the user, and we call it in parallel to visualize all the records. After this, we call the create canvas method again, which initializes the final canvas that will hold the final image. Then we call the merge function, which is defined by the user, to merge all these partial images in parallel into the final canvas. And finally, we call the write function, which takes this canvas and generates the final image that's displayed to the user. So now let me show you some examples of how we can define these 5 functions. Let's say we want to visualize satellite data. The first step is the smooth function. So the smooth function will actually take part of the data and try to estimate missing points. So as you can see here, there are missing points due to the clouds. And this function applies a 2-dimensional interpolation technique to estimate these missing points. Then the create canvas function will initialize a 2D matrix. Initially, they will all be zeros. These actually represent the different temperatures at different pixels of the image that you want to generate. Then the plot function will take one record, and depending on the location of this record at its temperature, it will update some entries in this matrix. Then the merge function is as simple as matrix addition, so it just adds up 2 matrices to each other. And finally, the write function will map each entry in this matrix to a color in the image, and then writes the final image to the output. So once defining these 5 functions, we can plug them into the abstract algorithm to generate this image at scale. Similarly, if we need to visualize a road network, which is a totally different type of visualization, we can still express it using these 5 functions. And now if the users want to add a new visualization technique, all they have to do is just to define these 5 functions, and then it runs automatically by Hadoop Viz to generate the image at scale. So users don't have to worry about the scalability anymore. So all of what I described now is a way to generate a single frame of the image, right? So we have the dataset, and they need to generate one image. Another way of visualization is what we call multi-level images. So multi-level images, you actually want to generate an image where users can zoom in and out to see more details of a specific area. This is actually similar to Bing Maps, for example, where you have like a very high level image, and then as you zoom in and out, you can see more details of a specific area. However, in our case, we actually are generating this data for a specific data set. So you have your own data set, and you want to generate this image. And this example, this one example, which is like 2 GB data set. And although the data set is not really huge, due to the huge size of the underlying image, it might take 1 hour in one machine to generate this data. While in Hadoop Viz, we can generate it in 2 minutes only. And without going into the details here, we actually, the basic idea is to generate this pyramid of image tiles. And as you generate more zoom levels, you can actually allow the user to zoom in more to get more details. So I'm going to get into the details here, but the basic idea is that we partition this pyramid into smaller parts and then generate each part separately. So we have a custom model to compare the different algorithms for generating this pyramid. And then we can parallelize the work using multiple machines. Yeah?
Can you visualize only the raw data or the result of a query?
Sorry?
Can I pose a query and visualize the result of the query?
Yeah, so you can definitely do this. If the result has some special attribute and then you want to visualize it, you can definitely do this. Yeah. So yeah, so as I mentioned, like all the queries that we run in SpatialHadoop run as MapReduce programs, and the visualization is the same case. So the visualization is just a MapReduce program. So the output of any MapReduce program can be fed as the input to the next MapReduce program.
Right. So basically, all of the, in some sense, all of these blocks of code are composing through HDFS, through reading and writing across to HDFS.
Right. So the input is always from HDFS, and the output is also in HDFS, which means you can feed the output of one query to the input as an input to the other query.
So the indexing is like an offline step, which you can't do on the result of a query because it's an indexing step.
You can still do it, right? So you can, like, let's say you build a Voronoi diagram, for example, and then index this Voronoi diagram. So it's something you can do still.
You have to pay the cost of the indexing in the pipeline, however long it takes to build the index.
Right, yeah. So if you are expecting to query let's say the Voronoi diagram or the Voronoi triangulation multiple times, maybe you can run a query on it. Run an index on it so that you have the data indexed.
How expensive is indexing the data compared to like doing a scan of the data?
In terms of query processing, or?
The latency of the end-to-end time. If I sort of want to suppose I want to do a query, some sort of query that involves looking at the entire data set, in Hadoop versus, but maybe the query isn't fundamentally complicated, I just have to look at all the data, versus the cost of producing an index. Is the index much more expensive to compute or about the same or a little more expensive?
So if you're talking about a MapReduce program, like if it's just a map phase, which you can scan the data and write the output, it will be much more efficient than indexing, because indexing involves also shuffling the data from mapper to reducers. Okay. But if you are writing a complete MapReduce program, it's not much different, because at the end, the indexing is just scanning of the data, but has to reshuffle the records.
So it's the shuffling part that's expensive, not really the index construction.
Right, exactly. Yeah, so I'm a little bit over time, so I'm going to go quickly over the application that we built using SpatialHadoop. And basically, what I want to show here is that actually SpatialHadoop can be used in real applications. And what I always say here is that if nothing else with the SpatialHadoop, we are actually using it ourselves to build these applications. There are other examples of other universities who are using also SpatialHadoop to build their own applications. So one application is called Shahid, which is a system for querying and visualizing spatiotemporal satellite data. So you can select any area in the world on this web URL, and then you can visualize it or run some aggregate or selection queries on it. Another applications use OpenStreetMap data. So it extracts the data out of the 500 gigabyte data sets from OpenStreetMap, indexes this data so it becomes available for users to query with just a few clicks. Another application is called MNTG, which is the Minnesota Traffic Generator. And this application, you can go to this URL, select any area in the world, and then the system will simulate moving objects in the road network of the underlying area, which can be used for testing and benchmarking your applications. And now, the next part, I'm going to go quickly over some related work to SpatialHadoop and some experimental results. So actually, we are not the only players in the area of big spatial data. There are many other systems that are trying to extend existing big data frameworks to support spatial data. And if I want to differentiate between SpatialHadoop and all these systems with just one statement, I would say that SpatialHadoop is the only system among all these that extend the core of Hadoop to make it available for MapReduce developers. So all the other systems are somehow rigid in terms of the types of indexing they support or the types of queries they provide. while Spatial Hadoop is very extensible. So you can add your own spatial indexes, you can add your own spatial operations, or your own visualization, which makes it actually very attractive for researchers or developers to add their own techniques to it, because you don't have to work, you don't have to stick with the amount of like operations or indexes that ships with Spatial Hadoop. Yeah.
Do you support a predefined set of indexes, or do you support extensible indexing? These are very different.
We support extensible indexing.
So you have APIs to, and people can build their own indexes.
Right. There are actually existing projects that people are adding spatial indexes to Spatial Hadoop. So you don't have to go through the whole pipeline or writing the whole algorithm for indexing. You just have to define like an interface, an abstract interface, and then this defines how the index will be built. So it's just like one class that you implement. Donald, yeah.
Maybe a related question. So if you modify the core of Hadoop, if the core of Hadoop evolves, do you have to kind of adjust Spatial Hadoop? Because that's the advantage, right? If you only sit on top, then the open source community produces new versions of Hadoop. You don't have to kind of, you can...
Well, that's a good point, right? So actually our current implementation is somehow ships as an extension to Hadoop. However, it actually like overrides some internal classes of Hadoop. Which means, if Hadoop is totally like they changed the underlying architecture totally in a way that's not compatible with the current architecture, then Spatial Hadoop will have to be modified somehow. However, we still somehow use some kind of extension or expand existing classes, so it can actually run with different distributions of Hadoop. So we don't have to stick with a specific distribution. So there are some examples that people run it on Hortonworks, which is another distribution of Hadoop, or Cloudera Hadoop. So it can actually run across different things, although we built it on Apache Hadoop.
A dependency on these things that you've extended that it probably is difficult to change them at this point. It would break a lot of people's hearts.
Right, Thanks, we take the burden of this and then we're trying to make it easier for other people. So let me, okay, you have a question?
About the indexing part. So can you update the index when new data comes in, or you have to review the index?
That's a good point. Currently Spatial Hadoop is sticks with the limitation of HDFS, which means that you cannot modify the files in HDFS. So currently the indexes are static. So once you write an index, you cannot modify it. You can of course rebuild it if you have new data sets, but you cannot modify it. We have an extension which I didn't describe here, which is ST Hadoop. It works only for spatiotemporal data. So if you're expecting more data to come with a recent timestamp. For example, you have like Twitter data, for example. And each day you have a new batch of records with a later timestamp. We support some kind of update for the existing index. But this is somehow limited to this kind of spatiotemporal data. But in general, if you have a spatial index and you want to add more records to it, currently this is not supported. This is one of the open problems that we are thinking of approaching in the future. So let me quickly show some examples of experimental results. So this actually shows the performance of range query. So as we increase the input size from 1 GB to 128 GB, we can, the performance of Hadoop keeps decreasing. This is actually the throughput of the system because it has to process the whole file, while Spatial Hadoop can limit the amount of data that it processes using the spatial indexes, so it can keep its performance. Other example is spatial join, and this actually shows you, gives some motivation of the different spatial indexes that we support in Spatial Hadoop. So you can see how the same query runs at different performance numbers with different spatial indexes for the two files. So this actually motivates people to add more indexes that can be more efficient for specific queries. Another part is like computational geometry work. So we can show you here how we can speed up different kinds of spatial operations or computational geometry operations in Spatial Hadoop. Finally, this is the visualization part, and we can show here how we can speed up different kinds of visualization types by just defining these 5 abstract functions. So now the next part, I'm going to go very quickly over other research projects that I have been working on. One of them is Hackathon, which is here in Microsoft Research with Paul Larson and Justin. Basically, it was motivated by the huge drop of the prices of main memory. I'm pretty sure you are familiar with it. So basically, the project that I have did was how to differentiate between hot data and cold data and try to migrate the cold data to a cold store so that we can reduce the memory footprint and keep the performance well. And this was actually integrated with SQL Server. Another part is Quill, which I did with Badrish and Jonathan. And basically, in this project, we started with Trail as a single machine streaming processing engine. And then we provided an API that can parallelize this work in the cloud. Other project is Nadif, which I did in QCRI. This is an extensible data cleaning system. So we have some dirty data and user-defined cleaning rules, and then the system applies these user-defined rules to clean this data. Another system is called Sphinx, which is a system that I did very recently. You can think of this as Spatial Impala. So Cloudera Impala is like a parallel database designed by Cloudera, and Sphinx tries to reuse the spatial indexes that we built in HDFS by using the spatial query processing on Impala and extends it to support these kinds of spatial indexes. So this is mainly for SQL processing of big spatial data. So now let me, in the last part, let me go quickly over some future plans of my research. So some of them are actually open problems on the current work that I did. For example, the visualization part, we can think of extending the abstraction to support other types of visualization, such as 3D visualization, for example. And we can also migrate the image generation process to other systems, such as Spark or Storm, so that we can support real-time visualization. Other part is to expand the query processing engine of Spark so that we can make use of the spatial indexes that we built in SpatialHadoop. And this will allow us to support like iterative analytics queries. Other things to support the, extend the spatial indexes so that they can support interactive data where we can add more data. So this actually related to the question you asked. So the current index are static, but we can actually, in the future, we can modify or expand these indexes so that we can add more data to the index. For long-term plans, I actually have an idea of having a unified big data interface among the, on top of the big data frameworks. And this is actually motivated by the huge number of open source big data frameworks, such as Hadoop, Spark, and the Impala. And actually, a question that I usually get from users is which one of these systems I should use for a specific application. And it's very challenging because first, there is an overlap in the functionality in these systems. For example, all of Impala, Spark SQL, and Hive can support SQL query processing. And there is no clear winner in terms of performance between these systems. For example, the paper that introduced Spark SQL last year in Segment is compared to Impala and showed that Impala can be faster than Spark SQL. Another paper that will be published in VLDB later this year is actually comparing Hadoop to Spark and showed that Hadoop can be faster than Spark. Although Hadoop is very old and known to be very bad, they showed that there are still case studies that Hadoop can be faster than Spark. So with this, actually, it's very challenging to decide which system to use. But the good point is that we don't have to choose one system because we can actually run all these systems together in the same physical cluster. Because all of these systems support HDFS as a file system and support Yarn as a resource manager, which means all of them can coexist in the same cluster. However, my plan is to build a unified big data abstraction on top of them, where users can express their queries in a unified language. And then this system will apply some cost model or some rules to choose which underlying system should be used for this specific query. For example, if it's like iterative query, it can run on Spark. If it's IO bound, it can run on Hadoop. We can also apply query optimization so that you can take this query and try to optimize it for the specific application or for the specific underlying framework that we chose. Or we can also apply some advanced query execution techniques. For example, you can take a huge or complex query, break it down into smaller parts, and run each part on a different framework, and then combine the results back together. And with this, we can actually provide a better user experience for users to use or choose between all these different systems. Another long-term project that I can work on is geographical distributed clusters. And this is actually motivated by the systems that generate a huge amount of user content. For example, think about Facebook or Twitter, where people create a huge amount of content. So we have these users all around the world, and they are generating a huge content. And if you need to store all this data in one data center, it cannot scale with the amount of data that we store. So what currently is done in these systems is that they have different data centers, geographically distributed among the globe, and each one stores data from nearby users. And this works fine for storing the data and retrieving it. But when it comes to analyzing this data, what they currently do is that they ship all the data they want to analyze into one data center and do all the query processing in this data center. However, this can work in some cases, but in some other cases, it's better to do part of the query processing on the different data centers and then combine the partial results together in one data center to get the final answer. And the challenge is that if you want to run Hadoop or Spark in a distributed cluster or a distributed environment like this, in a geographically distributed environment, these systems are not actually designed for this kind of query processing. So they might keep moving or shuffling data between different machines which are totally like separate in terms of geographic location. For example, you can shuffle data from Europe to the US, for example, which will reduce the query performance. And what makes it even more challenging is that there is a trade-off between the cost and the processing time. So what we are planning to do here is to expand one of the big data frameworks. It could be like Spark or Hadoop, and then try to modify its core so that it takes into consideration the geographic location of machines to try to optimize the query and try to balance the cost and the processing time. So I reached the last part of my talk. Let me quickly summarize the talk, and then I'll be happy to get your questions. So I first described the different spatial indexes that we support in Spatial Hadoop. Then I described different operations such as range query or spatial join or computational geometry operations. And then we described the visualization part where we can visualize data in both single level and multi-level images. And then I described some applications that we built using Spatial Hadoop. And then I went over some other projects that I worked on and described my short-term and long-term research plans, such as Unified Big Data API and geographically distributed clusters. So this, I'll end my talk here, and I'll be happy to get your questions. Thank you all for listening. Any questions?
What's the largest scale data set that you have tried your system?
So I'll give you two examples of large data set that we worked with. For vector data, where we have like points and polygons, we worked up to like 5 terabytes of data. For raster data, which is the satellite data, we worked up to like 30 terabytes of data. Although like we are working with our archive, which is like 1 petabyte of data, but we didn't have the capacity of machines to store all these data. So I took like 30 terabytes a sample of this data and worked with it. This is the largest I could get in the machines that I have.
Scale well in those cases?
Yeah, up to this number, it scales very well. So it's almost linear with these huge data sets.
When they moved up to the petabyte level, did they see the performance scaling you'd hope for? I shouldn't say expect, but that you'd hope for when you go from 30 terabytes to a petabyte?
I didn't try it, but it would be very interesting to try. Like I didn't have the resources to try the 1 petabyte archive. I didn't have the resources to do this, but it would be very interesting to try it.
Tell you.
Yeah.
Do these systems run I/O bound or CPU bound or message bound, or what exactly limits performance here?
That's a good point, a good question. Because actually it depends actually on the query that we are running. So some queries are I/O bound, such as spatial join, for example. So it depends on how much data we need to read from disk. Other queries, such as like computational geometry queries, especially the Voronoi diagram or Voronoi triangulation, which is very complex, these are actually CPU bound. So like most of the time is actually spent in computing all these different Voronoi diagrams and connecting them together. So it depends on the query actually. In the visualization, we found that it's actually network bound. With visualization, it's actually network bound, or it depends on the communication between the different parts.
I could ask a trill question, which is, if 30 terabytes you might run on a single machine.
If you have,
if you have enough disk, yeah.
If you have
so there are systems like that where you can run 30 terabytes. Would you? What would happen if you tried that? Number one, and number two, does that suggest perhaps other approaches to the problem other than sort of Hadoop-like approaches?
That's a good point. So again, it depends on the type of query. So some queries can run by scanning the data. In this case, you can run it on a single machine if you have 30 terabytes of data. Other queries actually require all the data to be in memory for processing, right? So it really needs to look at all the data. For example, if you're running a Voronoi diagram and you need to use the typical single machine algorithm, you actually need to load all the data in memory because it has to do divide and conquer and keeps merging the data together. For the type of query processing that is done in Trill, well, I think actually let me think about it. So in trail, for example, we can actually run, like if we use trail as is, I think it can work with the spatial data. But the good question is, how can we improve trail to work better with the spatial data? Right? This could be a good part. I think, for example, like storing the data itself. So if you store this data, like even in trail, you have to like store the data first and then read it, right? So it has to be stored somehow. If you have the control to store it more efficiently, then we can actually reuse some of the parts that we did here. For example, spatial indexing or spatial partitioning, it can still be applied in a system like Trail or Quill because it's more distributed. So we can actually, while you store the data in Azure Blobs, we can make use of the spatial partitioning that we do so that we can actually do the query processing. We can make use of this. One thing, for example, we can think of adding to Trail is like currently it's like somehow scans the data, right? So we have like batches and then you run each batch separately. A good part is like if you can have special boundaries for each batch, then this can significantly speed up the query processing. So it's just getting a batch of records and try to process on them. Let's say you get a batch and then you know also the boundaries of this batch. This can significantly speed up the query processing. So this can be parts that we can, part of this work can be actually migrated to a system like Trail or Quill. Any other questions?
You talk about spatial, but what type of spatial systems do you support? You have one support for planner or geodesic?
That's the point. So far we worked with just planar data. So even if we're using like geographical data like lat and long, we just assume that it's flat on a map. We didn't take into account, for example, if the data is on a sphere. But this could be something to, this could be an open problem that we work on in the future. For example, if in this case we can use like hierarchical triangular meshes instead of like using the normal partitioning because it's more efficient or more suitable for this kind of data. But so far we just work with planar data.
System that I have to support.
We didn't have this situation, So, but it's very interesting. We can work with in the future.
All right, let's thank the speaker.